Welcome to the chapter on centre of mass. So, what is centre of mass? We've talked about it very briefly in M1 when we were looking at moments. Moments was the only chapter where we really looked at things with dimensions. Everything else was always simplifying things down to a particle. In moments we did have to consider the size of things. However, we only touched upon it looking at the centre of mass of uniform and non-uniform rods. Now, obviously, there are lots of shapes in the world that we have to be able to deal with, and so we're going to extend those ideas. Essentially, the centre of mass is if we take a larger object and want to simplify it down as a point mass, where does that mass act? So, it's generally the centre of the object, where an object would rotate about if left to rotate freely, something like that. We'll have a look at how it comes into different parts, but I'll run you through the outline of the whole chapter first. So we're going to be looking at the first two sections are distributed point masses in 1 and 2 dimensions, before going on to look at plane figures, so various different shapes on their own, and then composite plane figures, so putting those various shapes together. The last two sections are going to be then using centre of mass, so when we're suspending an object and when we've got an object on an inclined plane. So let's jump straight into the first section, which is the centre of mass in 1 dimension. Voila. We're looking in 1 dimension, so what we're going to look at to begin with is called x bar. So for this example, we're going to look at a system of 3 point masses distributed along a light uniform rod. We're going to keep this very general, so we'll call this end of the rod O. We'll have our masses M1, M2 and M3, and these are at distances x1, x2 and x3 away from O. What we want to do is we want to take moments so that we can combine these 3 point masses as a single mass and find out the position of that centre of mass for the whole system. So at the moment, if we took moments, say we were going to take moments clockwise about O, we'd have the moment is force times distance, so the force of M1 is M1G x1 plus M2G x2 plus M3G x3. And strictly speaking, on our diagram, these, to make it a force diagram, should all have G's next to them already. So this is taking moments. Now, in the equivalent system, what we want is, for our light uniform bar, we've got 1 mass acting at 1 position, which we're going to call x bar. And that's where that x bar comes in. That is the position of our centre of mass. So again, if we took moments about 0 for this one, we'd get, putting our G on, mg x bar. Now we want these two systems to be equal, so we'll set them equal. So we've got m1g x1 plus m2g x2 plus m3 gx3 equals capital M G x bar. Now from this we can immediately see that every single term has a g in it, so they all cancel out. Simplifying down to m1x1 plus m2x2 plus m3x3 equals mx bar. Now the mass here, because we're looking at the mass from the combined system, if you resolved and said they have to be equal to each other, resolving vertically, you'd find that m1 plus m2 plus m3 equals m. So putting all that together here gives us x bar is equal to m1x1 plus m2x2 plus m3x3 divided by m1 plus m2 plus m3. Now hopefully you can appreciate from this, if we added more masses on, we'd get an m4gx4, down here we'd get an m4, and this row here would keep getting longer and longer, both of them. So what we do is we simplify it down to the most general case. So for any number of point masses, we say x bar is equal to sigma mi(xi) from I equals 0 up to n, where n is the number of masses, divided by sigma mi, again where I equals 0 up to n depending on the number of masses. If you can't remember what the sigma means, it's just the sum of, so the sum of the mass times the distance of each particle from a fixed point divided by the sum of the masses of each particle, and that will give you the location of your centre of mass. You'll have come across x bar in statistics before, looking at averages. That's essentially what we're looking at here. We're finding the x bar is the x coordinate of the centre of mass. Now as we're dealing in one dimension, we only have one. So here's a little explanation of how we find x bar. Here's the equation that goes with that. Just notice the one slight difference to that example. We've got I equals 1 to n on both sigmas, not I equals 0. Someone made a mistake, I don't know who. Terrible teaching. As with any good mechanics question, the first thing we're going to do is draw a diagram. So we're dealing with 4 masses. It doesn't say they're on a rod or anything, but giving us a nice line to put them on will help. We'll start with our origin again. We've got 4 masses. We've got a mass of 4 kilograms, so 4g, which is at 2 meters. We've got a mass of 2 kilograms, so 2g, that's at 4 meters, so I'm just going to put that as another 2 meters along. We've got a mass of 1g, which is another 0.5 meters along, and we've got a mass of 5g, which is another 1.5 meters along. So there's our diagram. Now we're just going to use our equation. So if you remember, the equation is sigma from I equals 1 up to n of mi(xi) over sigma from I equals 1 to n of mi, and that is equal to x bar, which is what we're trying to find. So we can see we've got our masses and our distances all ready to go. So let's just fire away. X bar equals MIXI. So let's do them in order. 4G, 4. We don't need the G because there's no G in here. I've put them on my diagram because it's a force diagram, but I don't actually need them in here. So it's 4 times 2 plus 2 times, don't forget the total distance now is 4, plus 1 times 4.5 plus 5 times 6. Now those distances can come straight out of the question. All divided by the sum of the masses, so 4 plus 2 plus 1 plus 5, which gives us, if we're being very thorough, 8 plus 8 plus 4.5 plus 30 divided by 12, which gives us 16, 20.5, 50.5 divided by 12. At this stage I would jump to a calculator and go 50.5 divided by 12, which gives me 4.21 meters, and that distance is from our fixed origin O. And that's all there is to it. I know that lesson was short and sweet, but essentially that's how you find the centre of mass in one dimension for distributed masses. So don't forget that formula. X bar equals sigma from I equals 1 up to n of MIXI over sigma from I equals 1 up to n of MI. That we will use a few times in various different forms for the rest of this chapter, and you'll need it for other bits of mechanics going forward. So any questions, just make sure you email me or ask me in the lesson.